In mathematics, a projective space can be thought of as the set of lines through the origin of a vector space V. The cases when V equals R2 and V equals R3 are the real projective line and the real projective plane, respectively, where R denotes the field of real numbers, R2 denotes ordered pairs of real numbers, and R3 denotes ordered triplets of real numbers. The idea of a projective space relates to perspective, more precisely to the way an eye or a camera projects a 3D scene to a 2D image. All points that lie on a projection line, intersecting with the entrance pupil of the camera, are projected onto a common image point. In this case, the vector space is R3 with the camera entrance pupil at the origin, and the projective space corresponds to the image points. Projective spaces can be studied as a separate field in mathematics, but are also used in various applied fields, geometry in particular. Geometric objects, such as points, lines, or planes, can be given a representation as elements in projective spaces based on homogeneous coordinates. As a result, various relations between these objects can be described in a simpler way than is possible without homogeneous coordinates. Furthermore, various statements in geometry can be made more consistent and without exceptions. For example, in the standard Euclidean geometry for the plane, two lines always intersect at a point except when the lines are parallel. In a projective representation of lines and points, however, such an intersection point exists even for parallel lines, and it can be computed in the same way as other intersection points. Other mathematical fields where projective spaces play a significant role are topology, the theory of Lie groups and algebraic groups, and their representation theories. Introduction. As outlined above, projective space is a geometric object that formalizes statements like parallel lines intersect at infinity. For concreteness, we give the construction of the real projective plane P2, R, in some detail. There are three equivalent definitions: the set of all lines in R3 passing through the origin. Every such line meets the sphere of radius 1 centered in the origin exactly twice, say in P equals and its antipodal point. P2, R, can also be described as the points on the sphere S2, where every point P and its antipodal point are not distinguished. For example, the point is identified with, etc. Finally, yet another equivalent definition is the set of equivalence classes of R3, that is, 3 space without the origin, where 2 points P equals and par equals are equivalent if there is a non-zero real number I such that P equals I a par, that is, X equals I za, Y equals I ya, Z equals I za. The usual way to write an element of the projective plane, that is, the equivalence class corresponding to an honest point in R3, is X, Y, Z. The last formula goes under the name of homogeneous coordinates. In homogeneous coordinates, any point, X, Y, Z, with Z a permel 0 is equivalent to X, Z, Y, Z, 1. So there are two disjoint subsets of the projective plane, that consisting of the points, X, Y, Z, equals, X, Z, Y, Z, 1, for Z a permel 0, and the consisting of the remaining points, X, Y, 0. The latter set can be subdivided similarly into two disjoint subsets, with points, X, Y, 1, 0, and X, 0, 0. In the last case, X is necessarily non-zero, because the origin was not part of P2, R. This last point is equivalent to 1, 0, 0. Geometrically, the first subset, which is isomorphic to R2, is in the image the yellow upper hemisphere, or equivalently the lower hemisphere. The second subset, isomorphic to A1, corresponds to the green line, or, again, equivalently the light green line. Finally we have the red point or the equivalent light red point. We thus have a disjoint decomposition, P2, R, equals R2 R1 point. Intuitively, and made precise below, R1 point is itself the real projective line P1, R. Considered as a subset of P2, R, it is called line at infinity, whereas R2 P2, R, is called affine plane, that is, just the usual plane. The next objective is to make the same parallel lines meet at infinity precise. a natural bijection between the plane z equals 1, and the sphere of the projective plane is accomplished by the gnomonic projection. Each point P on this plane is mapped to the two intersection points of the sphere with a line through its center and P. These 2 points are identified in the projective plane. Lines in the plane are mapped to great circles if one also includes one pair of antipodal points on the equator. Any two great circles intersect precisely in two antipodal points. Great circles corresponding to parallel lines intersect on the equator. So any two lines have exactly one intersection point inside P2, R. This phenomenon is axiomatized in projective geometry. Definition of projective space: the real projective space of dimension n or projective n space, Pn, R, is roughly speaking the set of the lines in Rn+1 passing through the origin. For defining it as a topological space and as an algebraic variety, it is better to define it as the quotient space of Rn+1 by the equivalence relation to be aligned with the origin. More precisely, Pn, R, equals /, where is the equivalence relation defined by, if there is a non-zero real number I such that equals. The elements of the projective space are commonly called points. The projective coordinates of a point P are xo. Xn, where is any element of the corresponding equivalence class. This is denoted P equals xo. Xn, the colons and the brackets emphasizing that the right-hand side is an equivalence class, which is defined up to the multiplication by a non-zero constant. Instead of R, one may take any field, or even a division ring, K. In these cases it is common to use the notation Pg, n, K, for Pn, K. If K is a finite field of order Q, the notation is further simplified to Pg, n, Q. Taking the complex numbers or the quaternions, one obtains the complex projective space Pn, C, and quaternionic projective space Pn, H. If n is 1 or 2, it is also called projective line or projective plane, respectively. The complex projective line is also called the Riemann sphere. Slightly more generally, for a vector space V, P, V, is defined as /, where two non-zero vectors V1, V2 and V are equivalent if they differ by a non-zero scalar I, that is, V1 equals I V2. The vector space need not be finite-dimensional. Thus, for example, there is the theory of projective Hilbert spaces. Projective space is a manifold. The above definition of projective space gives a set. For purposes of differential geometry, which deals with manifolds, it is useful to endow this set with a manifold structure. Namely, identifying a point of the projective space with its homogeneous coordinates, let us consider the following subsets of the projective space. By the definition of projective space, their union is the whole projective space. Furthermore, E is in bijection with Rn via the following maps. The hat means that the ith entry is missing. The example image shows P1, R, though. It is covered by two copies of the real line R, each of which covers the projective line except one point, which is the point at infinity. We first define a topology on projective space by declaring that these maps shall be homeomorphisms, that is, a subset of E is open if its image under the above isomorphism is an open subset of Rn. An arbitrary subset A of Pn, R, is open if all intersections AA copyright E are open. This defines a topological space. The manifold structure is given by the above maps too. Another way to think about the projective line is the following: take two copies of the affine line with coordinates x and y, respectively, and glue them together along the subsets xa permel 0 and ya permel 0 via the maps. The resulting manifold is the projective line. The charts given by this construction are the same as the ones above. Similar presentations exist for higher dimensional projective spaces. The above decomposition in disjoint subsets reads in this generality: Pn, R, equals Rna1 This so-called cell decomposition can be used to calculate the singular cohomology of projective space. All of the above holds for complex projective space too. The complex projective line P1, C, is an example of a Riemann surface. Projective spaces in algebraic geometry. The covering by the above open subsets also shows that projective space is an algebraic variety. It is covered by n+1 affine n spaces. The construction of projective scheme is an instance of the Proj construction. Projective spaces in algebraic topology. Real projective n-space has a quite straightforward CW complex structure. That is, each n-dimensional real projective space has only one n-dimensional cell. Projective space and affine space. There are some advantages of the projective space compared with affine space versus an R. For these reasons it is important to know when a given manifold or variety is projective, that is, embeds into projective space. Ample line bundles are designed to tackle this question. Note that a projective space can be formed by the projectivization of a vector space, as lines through the origin, but cannot be formed from an affine space without a choice of base point. That is, affine spaces are open subspaces of projective spaces, which are quotients of vector spaces. Projective space is a compact topological space, affine space is not. Therefore, Liouville's theorem applies to show that every holomorphic function on Pn, C, is constant. Another consequence is, for example, that integration of functions or differential forms on Pn does not cause convergence issues. On a projective complex manifold X, cohomology groups of coherent sheaves are finitely generated, O, the zeroth cohomology of the sheaf of holomorphic functions O. In the parlance of algebraic geometry, projective space is proper. The above results hold in this context too. For complex projective space, every complex submanifold X-Pn, C, is necessarily an algebraic variety. This is Chow's theorem. It allows the direct use of algebraic Eurogeometric methods for these ad hoc analytically defined objects. As outlined above, lines in P2 or more generally hyperplanes in Pn always do intersect. This extends to nonlinear objects, as well, appropriately defining the degree of an algebraic curve, which is roughly the degree of the polynomials needed to define the curve. It is true that any two projective curves C1, C2'Pn, K, of degree E and F intersect in exactly F points, counting them with multiplicities. This is applied, for example, in defining a group structure on the points of an elliptic curve, like y2 equals x3ax plus 1. The degree of an elliptic curve is 3. Consider the line x equals 1, which intersects the curve exactly twice, namely an and. However, inside P2, the projective closure of the curve is given by the homogeneous equation, y2az equals x3az2 plus z3, which intersects the line in 3 points, 1, 1 1, 1, a 1, 1, and 0, 1 0. Any projective group variety, that is, a projective variety, whose points form an abstract group, is necessarily an abelian variety. Elliptic curves are examples for abelian varieties. The commutativity fails for non-projective group varieties, as the example GLN, K, shows. Axioms for projective space. A projective space S can be defined axiomatically as a set P, together with a set L of subsets of P, satisfying these axioms. Each two distinct points P and Q are in exactly one line. Veblen's axiom: if A, B, C, D are distinct points and the lines through AB and CD meet, then so do the lines through AC and BD. Any line has at least 3 points on it. The last axiom eliminates reducible cases that can be written as a disjoint union of projective spaces together with 2-point lines joining any 2 points in distinct projective spaces. More abstractly, it can be defined as an incidence structure consisting of a set P of points, a set L of lines, and an incidence relation I that states which points lie on which lines. The structures defined by these axioms are more general than those obtained from the vector space construction given above. If the dimension is at least 3, then, by the Veblen-Euro-Young theorem, there is no difference. However, for dimension 2, there are examples that satisfy these axioms that cannot be constructed from vector spaces. These examples do not satisfy the theorem of Desargues and are known as non-de Sarguesian planes. In dimension 1, any set with at least 3 elements satisfies the axioms, so it is usual to assume additional structure for projective lines defined axiomatically. It is possible to avoid the troublesome cases in low dimensions by adding or modifying axioms that define a projective space. Coxeter gives such an extension due to Bachmann. To ensure that the dimension is at least 2, replace the 3-point per line axiom above by. There exist 4 points, no 3 of which are collinear. To avoid the non-de-Sargesian planes, include Pappus's theorem as an axiom. If the 6 vertices of a hexagon lie alternately on 2 lines, the 3 points of intersection of pairs of opposite sides are collinear. And, to ensure that the vector space is defined over a field that does not have even characteristic, include Fano's axiom. The 3 diagonal points of a complete quadrangle are never collinear. A subspace of the projective space is a subset X, such that any line containing 2 points of X is a subset of X. The full space and the empty space are always subspaces. The geometric dimension of the space is said to be n if that is the largest number for which there is a strictly ascending chain of subspaces of this form. A subspace in such a chain is said to have dimension. Subspaces of dimension 0 are called points, those of dimension 1 are called lines, and so on. If the full space has dimension, then any subspace of dimension is called a hyperplane. Classification dimension 0, the space is a single point. Dimension 1, all points lie on the unique line. Dimension 2, there are at least 2 lines, and any 2 lines meet. A projective space for n equals 2 is equivalent to a projective plane. These are much harder to classify, as not all of them are isomorphic with a PG, D, K. The de-Sargesian planes satisfy de-Sargesi's theorem and are projective planes over division rings, but there are many non-de-Sargesian planes. Dimension at least 3, 2 non-intersecting lines exist. Veblen and Young proved the Veblen-Young theorem that every projective space of dimension n A perm L3n is isomorphic with a PG, n, K, the n-dimensional projective space over some division ring K. Finite projective spaces and planes equals. A finite projective space is a projective space where P is a finite set of points. In any finite projective space, each line contains the same number of points and the order of the space is defined as 1 less than this common number. For finite projective spaces of dimension at least 3, Wedderburn's theorem implies that the division ring over which the projective space is defined must be a finite field, GF, Q, whose order is Q. A finite projective space defined over such a finite field has Q plus 1 points on a line, so the 2 concepts of order coincide. Notationally, PG, N, GF, Q is usually written as PG, N, Q. All finite fields of the same order are isomorphic, so, up to isomorphism, there is only one finite projective space for each dimension greater than or equal to 3, over a given finite field. However, in dimension 2 there are non-de-Sargesian planes. Up to isomorphism there are 1, 1, 1, 1, 0, 1, 1, 4, 0, a euro, finite projective planes of orders 2, 3, 4, 10, respectively. The numbers beyond this are very difficult to calculate and are not determined except for some zero values due to the Brucker-Euro-Reiser theorem. The smallest projective plane is the Fano plane, PG, 2, 2, with 7 points and 7 lines. Morphisms, injective linear maps T and L, V, W, between 2 vector spaces V and W over the same field K induce mappings of the corresponding projective spaces P, V, a P, W, via V, a, T, V, where V is a non-zero element of V and denotes the equivalence classes of a vector under the defining identification of the respective projective spaces. Since members of the equivalence class differ by a scalar factor, and linear maps preserve scalar factors, this induced map is well defined as problematic if V is non-zero and in the null space. In this case one obtains a so-called rational map, see also birational geometry. 2 linear maps S and T and L, V, W, induce the same map between P, V, and P, W, if and only if they differ by a scalar multiple, that is if T equals Is for some Ia perm L0. Thus if one identifies the scalar multiples of the identity map with the underlying field K, the set of K linear morphisms from P, V, to P, W, is simply P, L, V, W. The automorphisms P, V, a P, V, can be described more concretely using the notion of sheaves generated by global sections. It can be shown that any algebraic automorphism must be linear, that is, coming from an automorphism of the vector space V. The latter form the group GL, V. By identifying maps that differ by a scalar, one concludes that OT, P, V equals OT, V, slash car, equals GL, V, slash car, equals PGL, V, the quotient group of GL, V, modulo the matrices that are scalar multiples of the identity. The groups PGL are called projective linear groups. The automorphisms of the complex projective line P1, C, are called Ma paragraph bias transformations. Dual projective space, when the construction above is applied to the dual space var, rather than V, one obtains the dual projective space, which can be canonically identified with a space of hyperplanes through the origin of V. That is, if V is n-dimensional, then P, VA, is the Grassmannian of NA1 planes in V. In algebraic geometry, this construction allows for greater flexibility in the construction of projective bundles. One would like to be able to associate a projective space to every quasi-coherent sheaf over a scheme Y, not just the locally free ones. CEGAII, Chap. 2, Pa. 4 for more details. Generalizations, dimension, the projective space, being the space of all one-dimensional linear subspaces of a given vector space V is generalized to Grassmannian manifold, which is parametrizing higher dimensional subspaces of V. Sequence of subspaces, more generally flag manifold is the space of flags, that is, chains of linear subspaces of V. Other subvarieties, even more generally, moduli spaces parametrize objects such as elliptic curves of a given kind. Other rings, generalizing to associative rings yields the projective line over a ring. Patching projective spaces together yields projective space bundles. Sevrier-Euro-Brouwer varieties are algebraic varieties over a field K, which become isomorphic to projective spaces after an extension of the base field K. Another generalization of projective spaces are weighted projective spaces. These are themselves special cases of toric varieties. See also generalizations Grassmannian manifold, projective line over a ring, space projective geometry projective transformation, projective representation related geometric algebra. Notes. References, Afanasov, V.V., Projective Space, in Haswinkel, Mikhail, Encyclopedia of Mathematics, Springer, ISBN 978-1-55608-010-4, Baer, Reinhold, first published 1952, Linear Algebra and Projective Geometry, Dover, ISBN 978-0-486-44565-6, Butel-Spacher, Albrecht. Rosenbaum, Ut. Projective Geometry, From Foundations to Applications, Cambridge University Press, ISBN 978-0-521-48277-6, Mr. 1629468, Coxeter, Harold Scott MacDonald, Introduction to Geometry, New York, John Wiley & Sons, ISBN 0-471-18283-4, Coxeter, Harold Scott MacDonald, Projective Geometry, Toronto, Ont University of Toronto Press, ISBN 0-8020-2104-2, Mr. 0346652, OCLC 977732, Dembowski, P., Finite Geometries, Ergebnis der Mathematik und ihrer Grenzgebiet, Band 44, Berlin, New York, Springer Verlag, ISBN 3-540-61786-8, Mr. 02333275, Greenberg, M.J. Euclidean and Non-Euclidean Geometries, 2nd ed. Freeman. Hartshorn, Robin, Algebraic Geometry, Berlin, New York, Springer Verlag, ISBN 978-0-387-90244-9, Mr. 0463157, ESP. Chapters I2, I7, 25, and 27, Hilbert, D. and Cohn-Vossen, S. Geometry and the Imagination, 2nd ed. Chelsea. Mukai, Shigeru, An Introduction to Invariants and Moduli, Cambridge Studies in Advanced Mathematics, Cambridge University Press, ISBN 978-0-521-80906-1, Veblen, Oswald. Young, John Wesley, Projective Geometry. Vols 1, 2, Blaisdell Publishing Company. Ginn and Company. New York, Toronto, London, Mr. 01796666. External links, Westerheim, Eric W., Projective Space, Math World, http, planetmath.org. Projective Space HTML, Projective Planes of Small Order.